so if we go now to the shapes that you have not seen in the past, we need to go to those molecules that have either 5 or 6 domains. And that can happen, like we talked about with Lewis structures, because there's an empty D sublevel that can receive electrons from the S and the P, and so you can expand the octet and have more than 8 bonding electrons, or have more than 8 electrons total around that central atom. So first off, we've got the trigonal bipyramidal one. That's the one where you have 3 in the equatorial position and 2 in the axial position. So if all of them are bonding orbitals, obviously you get the trigonal bipyramidal. If one of them becomes a lone pair, what's going to happen with trigonal bipyramidal is the lone pair is going to come off at an equatorial position. Okay, so if I take one of these off, what I'm left with is something called a seesaw, because I don't know if you can see it in my hand, but it can go back and forth and back and forth like a seesaw. Okay, so that's because we've taken one off of the equatorial position. If I lose another bond to a lone pair, now I'm getting something, again, it's coming off another axial position, or I'm sorry, another equatorial position. I get something called T-shaped, okay? So if I turn it on its side, it looks like a T. So 2 equatorials are gone. I'm left with a T. And then if I lose another pair, now I'm back to linear because all of the equatorials are gone, so I only have the 2 axials. Okay, so in trigonal bipyramidal, you lose the equatorial electrons first. And so again, you can see the shapes. Notice in the picture they're showing you these lone pairs. And again, this angle is probably a little less than 120 because this lone pair is going to cause some repulsion. And it takes up more space. And then if we get to the octahedral, okay, we've got 6 pairs. So 2 electrons have been promoted to the D sublevel in order to get this to happen. So then you wind up with obviously 6 bonding pairs, you get the octahedron. If I lose one, I'm going to lose it from the axial position now. Okay, and so what you wind up with is, I probably should put it this way because it's easier to see, a square, so 4-sided pyramid. So they call this square pyramidal. And then the other axial comes off if I get another lone pair. So now it's planar, and it is square planar because they are 90 degrees instead of the 120 degrees, but it's still in a plane. Everything that's bonding is all in a plane. So 5 domains lose their equatorial first. 6 domains lose their axial first. And I guess if you think about it, it doesn't really matter what goes because all the angles are the same, but the way we visualize it is if you take the axial off first. And so there you can see the different shapes as well. Okay, so let's get into bond polarity now. Again, I love these pictures from the book because it lets you show where the electron density is going. Last year, we talked about symmetry a little bit. We talked about vectors and the pull of the electrons, where the electrons being pulled. Remember that in a bond dipole, they're always going to be pulled towards the more electronegative atoms. And so, you know, something that is polar is going to be very symmetrical. The bond dipoles are going to cancel each other out, so the vectors will cancel each other out. And notice that we've got electron density equally distributed towards the outside of the atom. The inside of the atom is positive, the outside of the atom is more negative. And remember, to show those bond dipoles, we do an arrow with the head of the arrow pointed towards the more electronegative atom and the tail of the arrow being the positive part. So in this case, carbon is less electronegative than oxygen, so electrons are being pulled out towards both sides. If it's going to be polar, you're going to wind up with the vectors adding up, and so you wind up with electron density more on one side of the molecule than the other. And you can see this really nicely in the picture. Oxygen is pulling both sets of electrons from the hydrogens, and so the hydrogens wind up being a little bit more positive, the oxygen winds up being a little bit more negative, and we can definitely say that there is a positive side and a negative side. We have a polar molecule. So again, overall, the polarity of the molecule depends upon the combined effect of the individual polar bonds and the shape. The shape is going to contribute as well. So what allows polar bonds to cancel? Well, again, we talked about the fact that you've got to look at the geometry, the symmetry of the molecule, having what are the terminal electrons? Are they all, or atoms, are they all the same or are they different? If one of these was, you know, hydrogen, and the others were chlorine, okay, this would be a non-polar bond. If we're looking at carbon here, this is a non-polar bond because it's a carbon-hydrogen. These three are polar, so overall this molecule would wind up being polar. So it depends on what the terminal atoms are. If they have different electronegativities, the chances are they very well may be creating a polar molecule instead of a non-polar molecule. What prevents the bond dipoles from canceling? Well, again, asymmetry. If you have an asymmetrical molecule, which is essentially what this guy is, the chances are it's going to be polar. If you have asymmetry because of non-bonding electrons, something like this is going to be polar. If you have lone pairs cause asymmetry. Anything with lone pairs is probably polar. Having different terminal atoms, like I said here, would be polar. So those are the kinds of things you want to look for. Even molecules who, based on electronegativity, seem to be nonpolar will have slight polarity if those lone pairs exist. So something like pH3. Phosphorus and hydrogen have the same electronegativity, 2.1. But because phosphorus has, where's my structure here? Because phosphorus has a lone pair of electrons, this actually is an asymmetrical molecule, and it winds up being a little bit polar. Electron density is a little bit greater at the lone pair than it is on the hydrogens. So pH3, bond-wise, electronegativity-wise, you would predict to be nonpolar. For all intents and purposes, it's going to behave nonpolar, but it is actually slightly polar. Okay, so something to remember for AP. Pairs of electrons, lone pairs, are going to probably cause asymmetry, which means you will then have a polar molecule. All right, so I got some examples here. A little hard to do with you guys being on a video, but we'll give it a shot. All right, so if we're looking, I'm hoping this is the first one that we do. Well, take a minute, pause, take a minute, see if you can predict the polarity of these five molecules, and then we'll go through and see what your answers are. All right, so hopefully you paused the video and you are back. So this is the first one. So HCl, hopefully you predicted it's definitely going to be polar. Again, I don't remember which way I went, if I went across or down, so we'll see. BF3 is nonpolar. All of the very symmetrical molecule. Asymmetrical, very symmetrical. So symmetrical, nonpolar, asymmetrical, polar. Next one I believe is the CCl4 in the middle. Hopefully you said nonpolar. Definitely everything, all the electron densities being pulled out to the center of the molecule would be the blue part, and the chlorines would all be red all around the outside. Going up to NH3, hopefully you can see that because of that lone pair at the top, electrons are being pulled up from hydrogen to nitrogen, so it will be polar. And then likewise, having odd atoms, you're going to have chlorine pulling the electrons towards it, so you will have a polar molecule there. All right, so you really need to practice this stuff. That's really the only way to get good at it. So you've got lots of work to do in the textbook with problems and worksheets as well. So good luck with it all. Realize that there's another slide left. So here we go. So taking a look at molecular polarity, these are the questions that you're going to want to ask. Does the molecule contain polar bonds? No, then it's a nonpolar molecule. That's kind of a no-brainer. If it contains polar bonds, then you've got to look at the symmetry of it. Is it asymmetrical or is it symmetrical? If it's asymmetrical, it's going to be polar. If it's symmetrical, it's going to be nonpolar. And again, the exception is slight polarity if you have lone pairs of electrons. So inherently, the stuff that are symmetrical are these guys. Unless you change the kinds of atoms that are on the end, if all the atoms are the same, if all the terminal atoms are the same, you're going to have very symmetrical molecules and therefore polar. Oops, forgot one, square planar. And if you have asymmetry, where you have lone pairs as a result, these are the shapes that are probably going to be nonpolar. I'm sorry, polar. So symmetry means nonpolar, asymmetry means polar. And again, even symmetrical shapes become asymmetrical if those terminal atoms are different that are attached to them, so be careful. And now we're done. So now head off and do some of the practice.